Okay, dynamic compression is the reason that this too high compliance in emphysema is a problem. Okay, and so here we have our cartoon respiratory system. The conductive zone of the airways is represented by the tube. The alveoli are all lumped together in one balloon, and this thing is the chest wall, and of course the pleural space is greatly exaggerated so that we have a place to write numbers. Okay, so we're at the end of a normal inspiration. Atmospheric pressure is 0. Alveolar pressure is 0. There's no airflow because there's no pressure gradient. Air has come into the lungs, but now the pressure is equalized. And if we look throughout the airways, the pressure is 0 everywhere. Okay? Now, we're still contracting our inspiratory muscles. The lungs have elastic recoil that's pulling away from the chest wall. Okay? And at this particular volume, the elastic recoil is generating a negative pressure of -12 in the pleural space. If we made a greater effort, it might be -16. Okay, so but at this specific volume, the elastic recoil is pulling inward with a force of -12. Okay, so let's now look at the transmural pressure. Trans is across, mural means wall. So across the wall of the airways, that's what we're looking at. So the transmural pressure difference is equal to the inside pressure minus the outside pressure. Inside is 0, outside is -12. So the transmural pressure is +12. Okay, the pressure inside is 12 higher than it is outside. And so the airways will stay inflated. This is good. Okay, so we were sitting here at the end of inspiration. Now let's begin expiration. Okay. Okay, so atmospheric pressure is 0. We have relaxed our inspiratory muscles. Elastic recoil of the lungs and chest wall is now moving inwards, and we're not doing any muscular effort, so the pleural pressure is 0. And now this is increasing the alveolar pressure. So we had -12 outside, a transmural pressure of 12. We have the same transmural pressure, but now the pleural pressure is 0 because we're relaxing our muscles, and the +12 is in the alveoli. Okay? So we now have a pressure gradient, +12 in the alveolus, 0 outside. Air will flow out through the airways. Okay, and as the air moves out through the airways, through the airway resistance, the pressure will gradually drop off to 0. Okay, so now if we look at the transmural pressure, pressure in minus out, +12, +9, +6, it's always positive. The airways will stay inflated, so that's good. Okay, now let's take a normal person but do a forced expiration. You're exercising, you're breathing faster, or you're blowing up an air mattress or a balloon. Okay, atmospheric pressure we always define as 0. Okay, now we're exerting a force with our expiratory muscles, our internal intercostals and accessory muscles. So we're actively compressing our thoracic cavity, and the effort that we're exerting is adding 16 to the pleural pressure. Okay, so we're squeezing the system. Okay, now we still have the same 12 from the elastic recoil of the lungs, but we're adding 16 to this by actively expiring, so that gives us +28 in the alveolus. Okay, so another way of looking at it is that at this lung volume, the pleural pressure will always be 12 less than alveolar pressure, and so if it's 16 here, it's got to be 28 here. Anyway, so we now have an alveolar pressure of 28, so we have a very large driving force for expiration. We're going to really force the air out quickly, And so as the air goes out, the pressure drops, okay? But you can see that at some point, it's now dropped to a point where the pressure inside is equal to the pressure outside. Below this, the transmural pressure is positive, but here's the equal pressure point, and above this, okay, above the equal pressure point, the pressure inside is less than outside, and so that's a negative pressure, that's a collapsing pressure. Pressure outside will be squeezing the airways to a narrower diameter. And this is dynamic compression of the airways, okay? And dynamic compression occurs in bronchioles. It doesn't happen in the trachea or in bronchi that are surrounded by cartilage, but in compressible airways, you see dynamic compression. Okay, and dynamic compression limits the airflow, and yeah, okay. So here's our flow volume curve, okay, and as a result of dynamic compression, this entire part of the curve is effort independent, and it's effort independent because at each point, if you exert a greater effort, you just compress the airways even more to a narrower diameter, and so it's a self-limiting process. You can't get outside of this curve because you just get more dynamic compression. Okay. Now this happens in normal individuals. It doesn't happen during normal breathing, but it happens with increased ventilation. Right. Okay. So, or, yeah, blowing up a balloon, whatever. Okay, so now let's look at emphysema. Okay, now here's what we had with the normal situation. Here we have a patient with emphysema. Atmospheric pressure is 0 at the end of inspiration. Airflow is stopped. Alveolar pressure is 0 all the way through the airways. No airflow. Okay. Now, we have elastic recoil of the lungs, and even though we're holding the lungs at the same volume as we did in the normal person, the elastic recoil in emphysema is much weaker than normal due to the high compliance, the abnormally high compliance of the lungs. Okay, so normal lungs pulled away from the chest wall, generating -12 pressure. Okay, the weak recoil in emphysema at this volume pulls away less strongly, and so we only have -4 in the pleural pressure. Okay, so now let's, so that's the difference in emphysema is that the elastic recoil is weaker. The pleural pressure will not be, it's still going to be lower than alveolar pressure, but it's not as much lower. Okay, so let's look at forced expiration in emphysema. Okay, so in the normal case, we're exerting a pressure of 16, compressing the lungs, and so the pleural pressure is +16 in both normal and emphysema. Due to the elastic recoil, this added 12 to the alveolar pressure in the normal case, but it only adds 4 in the case of emphysema. Okay, so instead of a gradient of 28 to 0, we now have a gradient of 20 to 0. Okay, so we'll get some airflow, but if we look at the transmural pressure, as the pressure drops going out through the airways, we can see that we've already gotten below the equal pressure point at this point, and here the pressure is much lower inside, and so we're going to have severe dynamic compression of the airways. Okay, and this is the reason that the clinical sign for emphysema is a slowing of forced expiration. Dynamic compression is much worse because of the weak elastic recoil of the lungs. Dynamic compression happens farther down in the airways, and it happens to a greater extent in emphysema, and no amount of effort can overcome this, okay, because this occurs in the effort-independent part of the curve. Okay, so our flow volume curves again, and the point here is just to reiterate that expiratory flow is compromised, and there's this little spike, and then it really drops down to the point where the expiratory flow is pretty much the same as what they had with normal tidal breathing, and they can't change this by exerting a greater effort because this is the effort-independent part of the curve.